And first, for this question, we are asked to calculate the MMF. So if you recall, MMF is magnetomotive force, and we can represent it by F sub M, or you remember that fancy written F that was used in the notes there to represent that. It is equal to N multiplied by I, which is the number of turns in the coil multiplied by the current through it. And a lot of the times I'll just use is MMF, whether it's lowercase or uppercase, to represent that, and then there's no confusion. Magnetomotive force then is equal to, back to our given information, we have 5 turns. Multiplied by the current was 2 amps. Now, a bit of a strange unit there for MMF, but it's amps times turns, right? So it is indeed 10 amp turns. We can do amps times a lowercase t, or you could write out turns. Okay, so the MMF is 10 amp turns. Now, for part B, we are asked to find the flux. And the flux comes from magnetic circuit Ohm's law, which says the flux is equal to MMF divided by the reluctance of the circuit. And reluctance, remember, was that fancy written R, or R sub M. And so we have 10 amp turns divided by the reluctance, which was given here. And reluctance, remember, amp turns per Weber is a small unit, so reluctance tends to be very large. 40 times 10 to the plus 3, so 40,000 amp turns per Weber. And so the unit of flux is usually very tiny, so you're normally into milliwebers or maybe even microwebers. And so if he does the calculation here, 10 divided by 40,000, you come up with 250 times 10 to the negative 6. And with respect to units now, amp turns in the numerator cancels with amp turns in the denominator. We're left with 1 over Webers. And so that means, of course, that our unit for flux is Webers. And 10 to the negative 6 can be replaced with a micro. So the flux in that circuit is 250 microwebers. Okay, now next then, if the solenoid is wired as shown, will the solenoid repel or attract the permanent bar magnet? And how can you tell? Well, remember, we had a right-hand rule for that, right? And a right-hand rule was wrap the fingers of your right hand around the magnet or the electromagnet in the direction of conventional current. And so, in this one, of course, the conventional current comes out of the DC source here through the positive terminal. And so down here then on the back of the magnet and around this way, and then of course this way, and so on, until it goes back to the battery. So if you're going to wrap your fingers around that in the direction of conventional current. You put your palm on the front of it where I have my red arrows, and your fingers would wrap around the back because the current is going down on the back of it. So your thumb would point left, and where your thumb points is the North Pole. And so that means that for this magnet, it's north here, south here. And so what happens to the magnet when we have two North Poles together? Okay, so the answer to this question here, and don't even ask you to explain really, will the solenoid repel or attract the permanent bar magnet? The answer is that it will repel. And we can go on to say then, since like poles are adjacent, because those two North Poles will push on each other or repel. Okay, so just let me fix that for a second there. I'm trying to say R there. Now, that was a J.